to explore. And so we're going to learn a lot about data visualization. We are going to learn about the use of pandas, which is a very important library. Okay, so let me share my screen here. So we are going to start with our known coding case. And can you see my screen correctly? And can you hear me? Amazing, great. So the title of today's case is...
works fine.
Great, thank you, Monica. The title for today's case is, should we develop a commercial snap test for predicting recovery from spinal cord injuries? So it's a very important topic. And one of the topics that we introduced in Thursday's lecture was the importance of visualizing our data. Data visualization can provide insight about the data content. However, it cannot be the only source of information for us. And data visualization has advantages and disadvantages. And at the end of this case, you will be able to look at a data science problem and choose and prioritize different sources of data visualization to help you inform better your decision as a data scientist, and ultimately to reach the right conclusions for your analysis. So before we start the case, let's start with the following exercise. So it's going to be a simple exercise, just so it's like a warm-up. When you go to the gym, before you start lifting heavy weights, you probably want to warm up your body a little bit, 5–10 minutes of light cardio. So and that's what we are doing today. And this is a historical data set, so an interesting case. So this is a map of the cholera outbreak in London from 1854. At the time, it was, it was considered a big deal because a lot of people were getting infected with cholera, and it, it was what was dominating the news. So the figure below shows the streets of Soho. Soho is one of the neighborhoods in London, and we have, with the yellow balloons, with the yellow dots, we have the instances of cholera cases. Notice that the circle are not the same size, okay? And we can see that the larger the circle, the higher the number of cases for that specific location. And the original version of this figure was constructed by a local clinician named John Snow. I'm wondering if this name rings a bell on your minds, if any of you are familiar with Game of Thrones. So if I would ask you, from this picture, identify the source of the outbreak. Yeah, winter is coming, hopefully though, not so soon. So the little drops indicate the water sources. Okay, so I'm seeing some answers right in the middle where there is the big circle, and you are probably correct. In fact, here, that street is called Broad Street, and indeed, that was the source of the outbreak. So from this map, the epicenter of the outbreak is clear. John Snow saw that this epicenter was located at the Broad Street pump, where Soho residents obtained their drinking water. So they were getting water that was contaminated with cholera. And the pump was closed and the outbreak eventually died out. So they were immediately able, from using data visualization. Can you imagine at the time, without having the instruments that we have today, this clinician, this doctor, was able to produce a map that identified, okay, this is where most of the cases are, so we should close this pump, and the outbreak of cholera was, greatly contained. So notice that Josno was not a data scientist, a statistician, or epidemiologist. At the time, these disciplines were still yet to be developed. However, he knew how the disease spread it out. So that helped. His knowledge about medicine helped understanding and making sense of this map. So that's an important concept of data science. Technical expertise needs to come with knowledge domain, with domain knowledge, which means with knowledge about the science, about the problem that you're trying to investigate. And this is the big difference between a data analyst and a data scientist. A data analyst is a specialist of analytical methods. A data scientist knows about analytical methods, but also about knowledge of the domain of the particular problem that we are studying, okay? Without the domain knowledge, it's harder to interpret results and to make sense of what we are investigating with our data. So let's start introducing our case for today. Animal models are commonly used to study spinal cord injuries in humans. So many times the knowledge that comes from the advancements in the veterinary sciences can inform also the medicine for human beings. So one of these developments that actually was originating from veterinary science was the development of a SNAP test. That is a test that just requires a single blood draw that will determine if the blood has the characteristics that will allow the individual to recover from the spinal injury. And this is something that can really help the doctors to understand what is the best way to treat the patient. If the information that we have from this test has enough predictive power, then the scientists try to market this product and to actually sell it so it can be used on a large scale. There is an alternative to a SNAP test that is more elaborate and more complex and potentially more expensive. That is a traditional lab test. Now, a traditional lab test requires lab equipment, requires more time for analysis, and so on. And that means that more time for analysis means longer time to make a decision about the patient and the treatment. So this is the context. So we are trying to investigate this SNAP test and if it's a good predictor of recovery from spinal injury. Now let's talk about the business problem, which helps for helps contextualizing from a practical standpoint the lifetime scenario where this can happen. So you are a consultant for a pharmaceutical company, and they would like to answer the following question. So they ask you, who is the consultant, to say, how well does SNAP test predict 6-month recovery rates, and should they be commercially developed? So the idea is this. The outcome that we want to investigate is recovery after 6 months. And we want to see if the patient after 6 months recovered, and then compare the recovery rates to what was predicted by the SNAP test. Notice that we do not expect perfection. Typically, tests have a number of false positives and false negatives. We will learn much more about this when we talk about statistical testing. But statistical testing is very similar in nature to medical testing, okay? Because it's associated to the context of risk. So from the analytical standpoint, so the business context is development of this test that can be or cannot be helpful. We have to determine that. The business problem is that you are working for a pharmaceutical company and you are asked to evaluate the efficacy of the test, the prediction of the test in 6-month recovery. Now, analytically, what are we looking at? What type of data do we have? Now, before we even dwell into data sources, being able to interpret figures is an important requirement, okay? So this case, we will approach it just by looking at graphs and seeing, okay, what can we understand from the graphs and the tables that we are going to see, okay? And so this is the structure of the case. We will start exploring some summary statistics. Remember, exploratory data analysis is the first step before we start analyzing any data. We see some plots, some basic descriptive plots, which are part of the exploratory data analysis, and then make a decision based on what we are observing in these plots. And finally, come to a conclusion about the predictive power of SNAP tests. Once we determine whether or not SNAP test is an effective predictive tool, then we can decide or recommend if it should be commercially distributed or not. Marlon is asking a very good question. To solve the exercise question, is it necessary to do a causal inference estimate? Well, of course, you know, when we are talking about clinical trials, now in this case, all the analyses were already performed, okay? And so this is a much simpler case. But typically when we are deciding if a test has diagnostic power, we do want to have a type of analysis that is robust under causal inference, so that where we can determine the link between correlation and causation. Now, if you have a proper control treatment design, that's already included. The causal link is already included because you have a controlled study. However, if it's an observational study, then you need further techniques. And causal inference is a growing field of statistics, and you know, you will get to explore it perhaps at a later time. So before we start seeing the graphs relative to this case, so we need to start deciding where do we look first. What is the sequence of plots that we should be looking at? And instead of looking at all the data at once or all the plots at once, we might want to break down the problem into smaller ones, okay? And also because the more complex your data becomes, the harder it is to observe everything at a glance, okay? So always start with one variable at a time, perhaps, or one question at a time, okay? So as a first example, before we talk about the SNAP test, let's revisit the previous exercise about the cholera outbreak. The question was, how can we stop or minimize the cholera outbreak given the information that we have? Now, that's a very wide question until you see the data, right? You don't know. So a sub-question could be, what is the origin of the outbreak? If we want to stop an outbreak, we might want to intervene at the origin of it so it stops spreading. Remember when COVID-19 started hitting, it was very important to understand where most of the cases were, to have lockdowns and try to limit the spread of the disease. At the time, we knew very little about how COVID-19 spreaded. It wasn't sure if it was spreading through the use of surfaces, if it was spreading through the air, if masks helped. We didn't know much. It's very different now. Right now, we have so many diagnostics, we have tests, we have a lot of knowledge. And of course, the vaccines are helping spreading the disease. But at the time, I'm sure you remember the dramatic images of Italian towns in lockdown, Wuhan in China in lockdown, and it was almost an apocalyptic scene. So a heat map can help understanding what are the hottest areas in terms of number of cases. And we can, if you click on the, actually see an example what heat maps are. Heat maps are maps that are geographic and that they have different colors based on the intensity of what you are observing. They are typically used for spatial point processes where you want to see the higher concentrations of a particular occurrence. They're called heat map because they typically use heat colors. So the lighter colors tend to be the higher ones, and the more red they tend to be the lower ones. They can have different, how to say, color gradients. Some of them, they can go from red to yellow. Some of them can go from red to blue to white, depending on the areas of risks. And Andres is saying heat maps are used a lot in sports. Absolutely. When you're looking at a basketball court and you want to investigate where the team has the highest chances of scoring, you see a lot of dots, and then the heat map will tell you where the team of your opponent is more dangerous. What do you want to do? You probably want to place the best defenders on those particular hotspots. Or heat maps can also be used. They are also used a lot in epidemiology, of course, to understand where the cases of diseases are, but also in they are used in astronomy to see where the highest concentrations of galaxies are. Now, typically, oh, there you go, Genesis. That's a beautiful heat map. Used in predictive maintenance of machine and vehicles, Sergio, you are correct. So heat maps are very, very popular and a very good tool in this case. So identifying the tool that you use to your data can be very important. So notice that also here we had that not only the dots were different in size, but they were also color-coded. So technically, this can be seen as an example of a heat map, although the heat maps tend to have like kind of a complete coverage. They try to interpolate everywhere. Here you are just seeing, you are seeing though that the different dots, the larger balloons are darker in color. So that's an alternative way of seeing a heat map. Nicholas, it can be used for time events. In which hour it's more affected? Absolutely, you can use a time map. You can be using a time contest in a unidimensional, and you want to emphasize, let's say, the peaks. You choose a different color. It's the same idea of heat map. The color can convey the idea of intensity and the idea of scale. Same thing when you're looking at maps to understand what is the higher concentration of volcanoes or where there is the highest seismic activity. There are many, many examples that you can observe. Or in meteorology, when you're looking at pressure maps, when you want to understand when you have high pressure and low pressure to understand how the weather is going. So, or when you're looking at global warming, you have a map of the globe and you see the hottest areas. Well, that's another example of color maps. I can go on and on because it's actually part of the classes that I teach, spatial data analysis, and I use heat maps a lot. Okay, so let's start looking at the data for what today's case is. So the investigators are interested in a snap test that will record levels of at the most 3 biomarkers. Okay, so this is where it gets a little bit technical, and we do not need to be biologists or chemists or or super specialists. We just need to understand the basics. Okay, so we are looking at 3 biomarkers that have this kind of arcane acronyms. The GFAP, the PNFH, and the S100P. for now, for the scope of today's case, now, keep in mind one thing: to become a data scientist or to become a specialist in a case, you need much more time than just a morning, a morning with me. So in today's lecture, we will not become experts about SNAP tests. We just need to understand the basics and to have the intuition and see how we can use data visualization, okay? So how do we get the data? Where do we get the data from? Researchers extracted data from medical records. So they are using historic data that were already collected on 31 dogs, okay, that had spinal cord injuries. Actually, I shouldn't probably not say that they are necessarily just dogs, because canines can be other type of similar animals, can be also wolves for what we are concerned. We don't know. We can say that they are dogs for simplicity, assuming that they are domestic animals. The clinical outcome of interest, as we were saying, is that if after 6 months did the dog recover from the spinal injury, each patient had blood drawn at the time of the injury. Remember, the test needs to happen early on. It needs to happen when the injury is present, and it has to tell you what are your chances of recovery, ideal, right? And from the blood that was drawn at the onset, we want to extract the level of these 3 biomarkers using a standard laboratory test. So the ground truth is the standard lab test. Remember that. So, you know, because we know that that test is efficient, it works. However, it takes, it's lower and it takes more time. So we want to use kind of a ground truth to validate the informative content of a SNAP test. So the extracted biomarkers represent the pre-treatment levels. So the patient was not treated yet for the injury. Okay, so we do not want that the treatment alters, you know, the conclusions that we are going to observe. So these are the first few rows of the data. See, a lot of you really like the heat maps, and I'm seeing some great images from maps and oh yes, the airflow on cars and the potential energy in the 2 problem body. Oh wow, that's I'm really happy that you are already playing around with tools and maps. Lizzie, yeah, to use heat map, the data are typically numerical, although you can sometimes you can also have qualitative scales. For instance, if you have a Likert scale, let's say from bad to amazing, and with all the levels in between, you can use also ordinal type of data to build a heat map. However, the concept of heat map is connected to the idea of scale. So from small to large, typically numerical. Sometimes you can have something qualitative, but still ordinal. Harold, why the question after 6 and not before 6 months? Well, because we want to see if we can detect the injury at the moment that it happens, and we want to check if the patient has recovered. We cannot go back in time. So we want to see if after 6 months the patient can recover. So the first few rows of the data set are as following. Remember, last time we talked about how using the command head, we were able to see the first few rows of the data set. So we have subject ID, that's our index right here. And then we have the 3 biomarkers. And then we have recovered versus non-recovered. This is the outcome after 6 months. And then we have here the sex of the individual. So the first 4 are females and the 5th is a male, okay? Now, the question is, would you consider fitting a model at this point? Why or why not? What would be your answer for this? Should we, Mauricio, first, the sample size is too small. Okay, that it's not very large. I agree with that. Do exploratory analysis first, Andres. First explore and no, absolutely. We want to understand better what to do, right? So all of these are very reasonable type of answers. Vlad, what kind of model is it referring to? Exactly. We probably want to discuss this, right? Is the sample size large enough? Well, that's a good question. Say a sample size of 30 may or may not be enough. Fabio points out that the fact, well, is this test more efficient in males versus females? That's a very, very legit question. And the answer is correct. All your concerns are all valid. For many, there are many, many reasons why talking about modeling after just seeing few rows of the data might be a little premature, wouldn't it? So one could be tempted and say, okay, yes, I could fit a logistic regression just to predict recovery versus non-recovery, or perhaps a classification method using machine learning. And however, at this point, it's definitely premature. It's way too early, so we need to look at the data more in detail to gain some intuition, identify potential problems, and then, only then, after we know enough, we can start working on formulating a model. Also because, remember, you are going to hear this sentence from me a lot. It's the famous quote by George Box that says, all models are wrong. Some models are useful. Remember, a model is always a simplification of reality. And if you are doing a simplification, there are many possible ones. And all of them can give you some insights about the complexity of reality. The question is, what model suits you better? What model helps you better understanding and answering your questions? Anyway, from an analytical standpoint, this particular example is a classification problem. That is, if our response variable is recover versus non-recovered, okay, we want to use our predictors, which are the 3 biomarkers, to identify what is the probability of recovery. In this sense, it's a classification problem because you want to classify which individuals are going to recover and which ones are not, based on the levels of the biomarkers. Now, probably from this table, you can start having a sense where this might be going. Can you see that the lower values of the biomarkers seems to be associated with potential recovery, while higher values seem to be associated to non-recovery. In particular, we can see this for the first biomarker, right? For the other ones, well, it's actually more debatable. Probably this one is not helping a lot. Maybe the PNFH, maybe we have to see. There are some high values here, but here there is a lower value. So the question can also become, well, what about you need a particular type of combination? Here is just 5 patients. We want to see more. We want to analyze the entire data set. So way too early, but at least you start generating questions. You start saying, okay, is what I am seeing for this first subject the same thing for everybody else, and so on. So we can start going from there. And then, of course, we might want to say, well, yeah, most of the subjects are females. Perhaps we need to see more of them and more males as well, just to see if there is a different type of interaction. So let's start looking at some summary statistics. Remember your beloved summary statistics from the previous cases: the mean, the median, the quartiles, the maximum, the minimum. All of these values help us understanding the data. Okay, so we have the results in the table below. So the GFAP value, notice that most of the time there are a lot of zeros on this one. Do you agree? Notice that the median is 0. So it means that we have at least 50% of observations that are 0, right? Because notice that, remember, the median is that value that leaves 50% of the observation to the left and 50% observation to the right in terms of magnitude. So we are saying that, there are at least 50% of zeros. The 75th percentile is 0.38, so it's still small, but then you have a maximum of 37.8. So definitely a distribution that has a very long tail to the right, very skewed to the right indeed. The other variables, the median is not 0. However, chances are that there are some zeros for both of them, perhaps, because the S100B, the minimum is 0, and for PNFH is actually negative. We will have to think about what it means, probably measured in a different scale. And somebody's pointing out at the fact, well, that value 37.8 can be an outlier. And it's true. However, if you look at the first examples of the case, you do see you still see that it's probably a data set that is highly skewed to the right, because you have values like 11 and 7 and 10 that are way, way larger than the median, which is 0. So definitely a distribution where the tail is not just outliers. There are some outliers for sure, perhaps, but there are also values that are just larger in magnitude, okay? And one says, what about the NANs? Well, we don't know yet if there are missing values or not in this data set. We will have to investigate more. So, exercise 3. The biomarkers all measure levels of biological elements in the blood. Do you notice anything unusual about the summary statistics of any of the variables? So did you notice something else besides what we have commented? Javier, a 90th percentile might be useful for that, indeed, because that helps us identify the tail. Very good, very, very good comments. S100B, according to Felipe, seems to be less skewed. I actually would agree, because I would actually agree, because it seems to be relatively well balanced if we look at the interquartile range. So the difference between the 75th percentile and 25th percentile, and the median seems to be centered there. The maximum is still a little bit, but it can be an outlier. Yeah. Angie, PNFH has a negative value. Great. So let's look at the answer. All of this, I can tell you already, there are excellent answers and very great comments. So the first, the anomaly we can say is that negative number that we had noticed. So negative numbers in markers that should be positive, they can be associated to different sources. And I'm telling you, what are some of the examples of that reason. Number one, sometimes variables get normalized or corrected. If there is a bias, then there is a correction that the data engineers apply. However, they apply it in the same way for all the data, and some data ends up being negative. Or they might be standardized with respect to their mean, and then they are in scores and so on. In that case, it's a relatively benign type of issue. Other times, negative values are put there in place to indicate that the data is missing. Typically, though, you don't have a number like negative 0.3. Typically, you have things like minus 999 or minus 99 or something like that to give you the idea that, okay, that data means that is an NA, the data is not available. Sometimes it can be just an error of perhaps you have a young intern that is not very expert and makes a mistake, and there is a typo, okay? And what do you do in that case? You go and talk to the expert, to whoever collected the data, and say, okay, what's going on here? Oh, that must be a mistake. Let's just let's just remove that one, or let's just use a 0, or maybe it's an error of the machine. There are plenty of things that that can happen. Unless you are a clinician, you may not even know that this marker could have been non-negative, and this error could have gone unnoticed if you just start analyzing it without checking, without doing an exploratory data analysis. And now this is a tiny data set. If you think about it, you only have 31 rows. Imagine if you have a large data set with hundreds or thousands of rows. You need to do some kind of exploratory data analysis and summary statistics to immediately identify a problem like this. Otherwise, you would have high risk of running a model, running analysis that will give you misleading answers. Okay? All right. Again, this is another example of domain expertise. And something as simple as the range and calculating the minimum can spot a problem like this. Now, imagine that there was not a negative number. Does it mean that the data set is error-free? No. And sometimes it's actually more dangerous when you don't see any error or anything wrong, because there might be something wrong and it's harder to detect. So, however, the only thing we can do is our best, right? Try to identify if there is a mistake using different techniques and so on. And then it can happen that data still contains mistakes. And this is why typically statistical models have an error term that can account for measurement error. Okay, we expect though that measurement error typically is how to say random, is not is identically distributed. So eventually we can cancel it out by using statistical technique. So yes, using domain knowledge and also, if I may say, common sense. Common sense can really help you in these situations. So another tool that we encountered on Thursday was the use of histograms. Histograms would tell us where the data is distributed, how the data is distributed. Is it symmetrical? Is it skewed? Is it unimodal or not? So remember, the histogram is on an XY chart where the x-axis is the variable of interest in its range and is typically divided in bins. There are most of the times the same size. And then on the y-axis, you have the frequency of how many instances of measurement for that specific interval you have. That's a histogram that is called in absolute frequency when you're just counting the instances. Okay. We said also that you can have a relative frequency histogram when you divide the number of instances by the total sample size, and that will give you percentages and say, okay, well, 50% of my friends are aged 40, between 40 and 50, and so on. So, that type of information. So taller bars on a histogram, it means that there is a higher frequency. Lower bars, it means that the frequency is lower. And here we have 3 histograms, one for each biomarker. Okay, so they're, in the way that it is displayed here, they're a little tall and super skinny, so it's harder to see, but we can see that, wow, for the first example, we have 25 observations that are between 0 and I would say between 0 and 3.3. And so definitely a very, how to say, not just skew distribution, but very spiky. It doesn't have too many observations in between, right? And then for the second one, which is the S100B, we see that there are less very small numbers, but all 3 of them we can see that they have a considerable number of zeros. or very, very low values. When we will talk about data transformation, we can see that one of the techniques that you can use when you have distributions of this type is to try to make the small number a little bigger and the bigger number a little smaller by using data transformation, like the log transformation. In this case, you couldn't use the log because you have a lot of zeros, so we have to do some other type of pre-adjustment before. But anyway, by looking at these histograms, the question is, are they really informative? Is this really the best instrument? Sebastian, should it be printed on the same scale for the 3 biomarkers? Well, the 3 different biomarkers are in very, very different scales, because you can see that the GFAP is between 0 and 40 on a scale between 0 and 40, and the other one is between 0 and 70. If you are referring to the y-axis scale, yeah, sure, you can see it, but here the numbers are also easy to follow because they are in absolute frequency. So remember, we are not just comparing the how tall each bar is, but we are also looking at the y-axis. In this case, I generally agree with you that the y-axis should be on the same scale, though. Jose, I would use box plot. Yeah, box plot would probably be more interesting in this case. Andres suggests the same thing. We have not introduced the box plots yet. Nicolas, they are informative. The question is that we can't apply asymptotic theory. Well, yeah, the sample size is small. And yeah, I mean, for basic questions, we can still do something with this data. We don't need necessarily to apply the central limit theorem and asymptotics. Violin plot. I like violin plots too. They can be used. Omar, there is no correlation among variables. Okay, that's interesting. David, we are not considering the sex of the patient. All of good points. So, as you suspected, the histogram, although interesting to look at, we can still look at it, it does not tell us much, except all the 3 biomarkers, they have a big spike at 0 or very close to 0. This is not surprising because we already knew that by just looking at the table and the first quartiles and the median, that for at least one of the markers was equal to 1, it was equal to 0. So, you know, we knew this. So another tool that I would like you to consider is the one-dimensional scatter plot, which is an alternative to a histogram. A bubble plot could be another one, as has been suggested, or the violin plot. However, yeah, the violin plot and the 1D scatter plot are actually somewhat related. So why do we use the one-dimensional scatter plot as an alternative to the histogram? And the one-dimensional scatter plot is used when you have a lot of values that are clustered together, that are very close to each other, and that they get bunched up under the same beam, okay? On this type of plot, the y-axis represents the quantity of interest, in this case, the level of the biomarker that you are considering, and the observed points are placed such that their y-coordinate equals their biomarker's value, and they are clustered as tightly as possible along the x-axis without allowing them to overlap. So you can really see the density of the points near where they cluster, okay? So the clusters of points will be displaced horizontally. So they are altered a little bit horizontally, although very close to the value, let's say very close to 0. And we have here the 1D scatter plot for the logarithmic transformation of each of the biomarkers. Notice that when you take the log transformation of variables that contain zeros, as I was mentioning, you cannot do it right away because the value of log at 0 is -infinity. So you want to add 1, okay? So your baseline becomes 0. So that's why you have here the log of GFAP plus 1, the log of S100B plus 1, and the log of the other marker plus 1, okay? Carlos, are there 1D heat maps? Yes, they are also called, there's also another type of plot that is called the carpet plot. That is actually similar to this, except it uses like little vertical lines, or you could use honestly a color, right? You could have here rows of pixels of different colors, right? And with the color changing with the number of points that you have. You know, there are many, many different choices for this. And Christian is saying, it looks like a violin plot. Yeah, and that's why I said that they are somewhat related. Now, here you can see from the first one that you have several zeros that are, you know, slightly altered, right? And you can see, you can have a better idea of the distribution of the data. You can also think about this by looking at sideways, and it almost looks like a histogram. If you imagine that to stack the points that are nearby, one on top of the other, you obtain sort of a dot plot, which is another alternative. If you look it up, the dot plot is another way to look at the distribution of the data. So keep in mind that here you have a log transformation, and it's only for visual purposes. And again, is to look at the data in a more precise way, to avoid, because the scales are really, really too different. You have so many values that are close to 0, and then you have value of 37. You need something that it's, you know, that allows you to look closer at the smaller data. We will talk a lot about data transformation. There are many cases that Correlation 1 has developed. I taught actually several of them. So it's possible that we will see each other when we talk about transforming the Y variable and the X variables in the linear regression context, for instance. So we talked about the distribution data and color. Color is a topic that came up already when we talked about color maps. However, color can be used also to investigate distributions, like in this particular case. From these plots, we can see that the GFAP has a large cluster at 0, while PNFH has more points, but only 1 0. Now, reconnecting to the original question, whether or not these biomarkers may be predictive of recovery status, we can color each point according to the recovery status. That is, we can say, okay, let's color the yeses and the nos differently, so we have a better idea of which biomarker is informative. So let's color in red the patients that recovered, and in black the patients that did not recover. Ruminger is asking, the log is natural log or a log base 10? It's a natural log. Typically we use natural logs. When you see the symbol log 10, then it is the logarithm in base 10. I know that in our algebra classes, they always tell us to write log E or log N, but in scientific literature, if it's not noted otherwise, always assume there is the natural log, okay? All right, so what do we observe here? From the plots above, which biomarkers do you think affect the likelihood of recovery the most? Just look at these 3 plots and just look at the way that GFAP, okay. Yes. NFH might have also some informative content, very good. Very good observations. So why not S100B? Right, right. Dispersion. Well, can we see that for high values of S100B, we have both black dots and red dots. So this is not telling us much, right? While here, the GFAP is telling us, well, for values above 2, okay, we know that there are few black points. However, there are some black points here too. And for the MPFH, well, also we have a little bit of confusion. So perhaps a combination of both might be something that we might want to look at, right? So it's a little complex, but if we want to look at the absolute counts of, we can see that most of the time, most of the times, you're not going to recover if the GFAP is high. Although the GFP could be low and still not recover. So, it's not a clear-cut answer. So we can only make statements in terms of probability of recovery. So the figure suggests that the subjects with low values of GFAP are more likely to respond, where the other two biomarkers are a little bit less informative. We still have to include the important piece of information, which is the sex of the individuals. Below, we show a parallel coordinates plot split by sex. What is a parallel coordinates plot? Here, I encourage you to read more about the different plots, when they're appropriate, when they are useful. And they are typically used for comparisons. And each vertical bar represents a variable, and with a unit that can be actually different. So for instance, this is a particular example of the iris dataset. It's a classic dataset that is used a lot for classification testing of machine learning methods and support vector machine, random forest, and other things. And as we see here 3 variables of interest: the petal length, the petal width, the sepal length, and the sepal width. And you have 3 different species, and you can actually see if there is a pattern that connects the 3 different variables. So how do we map this here? Well, we can see it in this way. So we have 3 different biomarkers in vertical and the values, and we have 1 line for each subject, okay? And the color code is still the same that we had before. In red, we have the recover. In black, we have the non-recover. And among the males, what do we see? That most of the patients that recovered, the males, had a low GFAP base and a high S100 base. Isn't that interesting? And the PNFH is typically low also when they recover, except for 1 case. However, even this extreme case has a low value of GFMP and a relatively high value of S100. While the ones that did not recover, okay, typically had a very low value of S100. Notice that all 3 of them are playing in concert. So a test wants to look at all 3 of them. By themselves might not be tremendously useful. However, in a synergic way, we can actually get a much better test. What about female? Well, female is more complicated, I would say, in the sense that most of the females that recover had a low GFAP, but some of them had it high. And also in the S100, we see that there is quite a bit of dispersion. However, for the female, the PNFH seems to be very informative for the probability of recovery, although there are several cases of no recovery that are more uncertain. So definitely the situation seems to be less clear-cut when it comes to females. So there's another way that you can look at things, and it can start giving you an insight about the differences between males and females. So indeed, they respond differently in terms of recovery to different levels of the biomarkers. Also, we can see that there is a difference in sample size between males and females. The female subset is larger in this particular case. Now, let's look at two-dimensional scatter plots. Two-dimensional scatter plots, you're very familiar with them. You have seen them everywhere, but scatter plot is a simple cloud of points of an X, Y variable. For instance, this is an example of a scatter plot. You have the ground living area. So here you have ground living area partially explains sales price of apartments. Of course, right? Larger apartments is going to be more expensive, right? Then, of course, there are other confounding variables that we can consider. How new is the apartment? How is it furnished? The quality, the neighborhood. There are many, many things that can play a role. But typically, if you want to have a bigger place to live, you're going to pay more. Kevin says the parallel coordinate plot is not recommended for large data sets. Well, yeah, you have a point, because the lines become way too crowded. However, you can use some of the techniques that we have discussed to actually color code the lines themselves by having the intensity of the same color telling you where there are more lines. One trick that I use, sorry for the little aside, but one thing that I do is when I have a lot of lines, and I do this a lot in time series, I use a very, very thin size for the line. And basically, when there are many of them, they become much thicker in the plot. And so you can identify where most of your data are. So that's another thing that you can do. You can do that also with scatter plots. You can use very, very small dots when you have a large data set. And you have less areas that get completely colored like this, but you will get more of a sense where most of the concentration of your points are. Anyway, the two-dimensional scatter plot is a plot where you are looking at two quantitative variables, typically on the continuous scale, and you have a y-axis and an x-axis. In this case, we can see by the orientation of the cloud of points that the sale price tend to increase with the size of the house. Okay. So what we are going to observe now is a particular type of scatter plot, which is a little bit different, to help visually identify the regions of the space where we observe a higher chance of recovery. We design a grid of points. So this is not like a scatter plot like the one that we have just said, but we are going to color them to the nearest point corresponding to an observed patient. So wherever there is, let's say, a black dot, okay, it means that that patient did not recover on that, and we are going to add a little black dots nearby, because we are assuming that for this combination of, let's say, of these two ones, of these two biomarkers, that's the thing, we have three biomarkers, so we cannot put them all in a two-dimensional scatter plot. So we will have to look at, so we will, just by using the nearest neighbor principle, we are going to say, okay, here you have two dots that are of different colors, and you can see it very well. The closer neighbors to the black dot, they are also going to be black. The closer neighbor to the red one, they are going to be red. So we want to see, okay, what is the recovery area? For which combination of values are we observing a high chance of recovery? And well, here we have a very dark, very black area, right? And it's typically when both, okay, is when GFAP is large. We already knew that. But so when GFAP is larger, we know already that the chance of recovery is small. What about when GFAP is small? Well, we can say that the chance of recovery is high as long as you know, it really depends on the area, on the S100B. There are some areas of S100B for which it might not be as straightforward, and we can see some areas here. So how many neighbors are we using? So we designed a grid of point, and we are considering the distance between each point in the grid and the observed data point. So we can also split them by gender, right? So we can have the male subjects on the left and the female subjects on the right. Now, for females, we can pretty much say that the chance of recovery is high for all values of S100B if the log GFAP is small enough. So if the log GFAP is small enough, the chances of recovery are high. However, if this S100B is high, we might see some issues, right? Like in this particular case and this case. Males seem to have always a pretty good chance of recovery, except if the GFAP is less than 1, okay, and the S100B is larger than 0.5, I would say, because that's the area where you observe some less likely chance of recovery. So what are the conclusions can you draw from the two scatter plots above? I told you some of the ones that jumped to my eyes. Don Diego, it is called scatter plot, but it looks more like an area graph for me. I would actually tend to agree with this. It's called scatter plot just because the dimensions are not, let's say, geographic. They are indeed the scale of the biomarkers, but it is really used as a map. So I would actually, yeah, so it's definitely there are principles of the data visualization, the map visualization that we have discussed. Very, very good point. Carlos, how can we say that the quantity of data is enough? Well, of course, we will have to do modeling and standard tests for that. At the moment, we are just exploring. None of this is a definite conclusion. Yes, recovery and gender, according to Yesid, is relevant. Yeah, we can see that the plots actually look quite different. One of you actually showed a nice example of a 3D scatter plot, Herman. Yes, I actually used 3D scatter plots in one of my papers. I find them that's sometimes useful from a descriptive standpoint, but they flatten at least one of the dimensions, so they are not always super reliable. Ideally, when you have a 3D scatter plot, you might want to look at the same graph, change the angles of the visualization, and that can help you having a better idea. Using a heat map would be easier. That could be actually interesting because we might actually, instead of using reds of the same scale, we could use a color gradient between red and black. Yeah. Isn't adding color 3D, says Andres. Yes, it is. But then the plot that Herman showed us essentially becomes 4D, right? Because you're also using the color. fiber. What is the key to decide what type of data visualization we should use in our analysis? The expertise, or when the observation does not coincide with our hypothesis? I think that the question that you are trying to answer is what should lead you to the type of data visualization that you should consider. In this case, you have 3 biomarkers. So chances are is that a combination of the biomarkers is going to give you the best answer that you need. So for this reason, we want to use plots that put these biomarkers together to compare them and to see how their combination works. This is why the use of the scatter plot. So the color contrast between male and female is striking, with the scatter plot for the male subjects being nearly all red and the plots for the female subject being mostly black. However, the sample sizes are small and large regions of these data points contain no data. Thus, any generalization from these figures must be done with caution, as you have pointed out. Henry, is there some difference between heat maps and surface response plots? Yes, yes, and the topic is actually kind of complex when it comes to surface response plots, but they do contain a lot of similarity. Is the type of informational content that changes. And Luis says, could a 3D scatter plot help? Indeed, it can also be used in this case. Perhaps you can look at all the 3 biomarkers at once. And here you have some scatter plots for the other combinations of remember, you have 3 of them, so you can have 3 different pairwise combinations. So we started with the GFAP and S100B. So we want to see now GFP versus PNFH, and then S100B versus PNFH. I find this particularly useful because the PNFH for male seems to provide no real informational content. Notice that, you know, almost the entire plot is red. However, for female subjects, the PFNH seems to, in conjunction with GFMP, seems to actually provide quite a bit of insight. And this is the NPFH versus the S100B. We can clearly see a nonlinear relationship here, especially for the female subjects. And this would be very hard to use for classification. Exercise 7. If the cost of the SNAP test depends on the number of biomarkers it uses, which biomarker would you recommend be included in the test? GFAP. GFAP for male. All right, so it seems like we have a huge consensus about GFAP. And the answer of the text, indeed, as all of you are correctly pointing out, is we would recommend collecting data from the GFAP only, as the other biomarkers seem to provide little additional information in terms of predicting recovery. And if there is information, we would need a much larger sample size to detect it. Now, keep in mind that this test could be potentially used as a pre-diagnostic test. It doesn't have to be the test that actually confirms a diagnosis. Sometimes we use these smaller tests just to have a clear idea if we should look further into it and then recommend further testing. My first manuscript that I wrote as a graduate student was actually using exploratory tests to detect cancer to detect breast cancers. So by just interpreting screening radiologists, and it would be a very non-invasive type of test that would identify cancer just by looking at this particular test. Now, if the radiologist would see a suspicion of cancer, then there would be a biopsy, which is a much more invasive type of test to recommend as a follow-up. The same thing when you get tested with a rapid test for COVID-19. The rapid test is not confirmatory. However, it tells you if you should follow up with a PCR, with a real, with a more sophisticated type of test to determine if you have COVID-19. The same thing would be for the SNAP test. The SNAP test could be a first test, and then if the GFAP levels are high, then perhaps you might want to go and follow up with a further test. What should the next step be? For example, would you recommend running a follow-up confirmatory trial or biomarker prediction accuracy? So yeah, among these two, which ones would you consider? Because all of the two, both of them, right, would be interesting in theory, but what about what to do first? Confirmation trial. Okay, more data. Get more data. You really think like statisticians. I like that. It makes me happy. I like more data. Other biomarkers. Okay. Very good. Now, more data would be desirable, but the first question would be, is the information that GFAP providing statistically significant? Can we do, let's say, a logistic regression and determine how effective it is? So a classification model could be a good potential next step before providing further recommendation of further confirmatory trials. Typically, this type of studies with small sample sizes, they're called pilot studies that then lead, they can be used as a justification for further investigation. That's, at this point that scientists publish their results and they say, okay, in a small study, we observed this. We need more funding for a larger study. So a classification study typically works like this. You determine a threshold that is a threshold for the variable of interest that will tell you above or below that threshold if the outcome is more likely to be recovery versus no recovery. This is just a logistic regression. Yes, logistic regression is probably the first classification model that you will encounter. Okay. And how might you fit a classification model to the study? What are the potential pitfalls associated with these studies? Yes, Lizzie, the answer is indeed binomials. Bernoulli, in fact, is 0, 1. Yeah. Herman, it's just an experiment to support a pitch to do a more formal research. But yeah, of course, it's very important, though, that this initial research provides at least some trends, some possibility of. And sometimes, don't get me wrong, sometimes small studies might give suggestions that then end up proving to be not true on a larger sample size. Also, we need to consider that how good was the sample, how well randomized it was. Were all the individuals of the same breed, for instance? We don't know. Maybe different types of dogs, might recover differently, different ages. We don't know that. We don't know what type of nutrition they had. There are so many different factors, and that those are typically things that you investigate with a larger. Okay, type of accident they have. Excellent point, Laura. Some of you are already suggesting a possible threshold. Felipe says C equal to 0.5. Okay, we'll see if that's good. Regularization, well, typically we use regularization as an excellent suggestion, typically when we have more variables though, right? In this case, we only have 3 or 4 at the most, if we are using the sex as the additional variable. Age would be interesting indeed. We know that chances of recovery diminish with age. Decision trees. Oh, some of you are already very sophisticated in terms of the models that you have encountered. All right, so potential pitfalls. We have already identified some of them. Well, another potential one is the location where they were collected. The subjects of the sample were dogs that were taken to the hospital by their owners. We didn't know that. Thus, they may be more likely to come from homes with resources, so availability of care, food, and veterinary help to support their health and so on. So this model, whatever we would end up using for this data, would be only very specific to the data set that we are using. Okay, and of course we have already determined that there are some differences between males and females. All right, let's see how we can extend our test. Upon further consideration of standard treatment protocols, your researchers have decided that critical treatment decisions should be made within 72 hours post-injuries. Consequently, they are interested in whether or not taking 3 measurements, 1 per day, might provide better predictions of 6-month recovery. Because GFAP was our most promising biomarker at baseline, let's first make a parallel coordinate plot of GFAP at regular intervals over the first 72 hours. Days 0, 1, and 2. To make the plot easier to parse visually, we split it by recovery status. So now you have, for GFAP, you have 3 different measurements. At the day of the injury, 1 day after, and 2 days after. And on the left plot, we have the dogs that effectively recovered, and on the right plot, we have dogs that ended up not recovering. So, what do you observe here? Take a few moments to look at these plots. Remember that before we were just considering the GFAP at the beginning. So remember, cases like this, can you see this? These three cases here, they were low on the day of the injury, and they ended up not recovering. But what happens? That those levels went up, right? So the stability of low GFAP seems to be an excellent predictor of recovery. And if at any point in time during the next 72 hours, they go up, that can actually be a formidable way to identify low chances of recovery. You might have cases like this particular one where the GFAP went up and the dog ended up recovering anyway. But again, we have a very small sample size, and so it could be a particularly young dog that was. Oh, excellent question. What are the lonely points mean? Well, that for them, they were actually not measured at subsequent times. So missing value. Also here, you see that lines with lighter color, those are observations for which we only had 2 measurements, but not the third one. We have the same instance here. So Camilo, no, the best idea would be to take them both, like to take the 3 of them and just see how stable they are. Because from what we are observing is that even if they are low at the onset, but then they go up, well, that's a sign of injury, especially when they go up. Fabian says the long points are for those that didn't make it after they. Not necessarily, it could be just that they were not measured. So the preceding plot suggests that the GFAP levels tend to be more volatile among patients that did not recover versus those that did, and that their peaks are higher. Below, we show a one-dimensional scatter plot of the maximum log GFAP at over 72 hours colored by recovery status. We see that can almost perfectly separate the data using this quantity via a classification method with a threshold of about 0.5. Remember, this is in the log scale, okay? Except for 3 points. Well, now we can see that just by looking at the maximum of 72 hours, we get a much better separation between the red dots and the black dots. So if we have the threshold as 0.5, the 0.5 would go right here. And so you would only have 3 cases that actually will recover, while you still have 1 point here that did not recover. So yeah, we also have to consider what is the, so let me give you, since we have a little bit of time and we are almost finished with the material of this case, which is actually a little short. Let me give you a little bit of insight about what can go wrong with this test. Well, this test can give you 2 types of wrong answers, right? It can give you the wrong answer in the sense that the test says that you have high chance of recovery and your dog does not recover, or that the chance does not have, the dog does not have a chance to recover and ends up being recovered. So you have false positives and false negatives. Which ones would be the most concerning? Right, if with positive we say that right, false positives are always the most serious type of concerns, right? Because you might end up like giving the wrong treatment, and that sometimes can lead to very invasive procedures or very. So yes, saying that you're sick when you're not sick is always more dangerous. And it's something that it's a concept that you will need to get more familiar as we go in. This test, though, as a preliminary test, can at least help us identifying a gray area where the conclusions are not super sharp and they need further investigation. So let's say if the values are on the log of the maximum +1 are above 0.5, okay, then we might say, well, we recommend further testing just because this marker has been high in the last 72 hours, and this is a potential for further complications down the road. For these reasons, this test could still be useful and could even still be considered commercially upon further studies, as long as we use it with the motivation that we can recommend further testing whenever needed. Okay. False negative, because you could die if you do not receive a treatment. Well, here we are talking about something a little bit different, Elliot. Here we are talking about the chances of being able to walk versus not being able to walk. So the C is the classification threshold that determines whether or not the biomarker was above a certain level that was affecting recovery. So let's look at some of the conclusions. We evaluated the potential market value of a SNAP test for spinal cord injuries in dog. We found that the biomarker GFAP seems to be the most discriminatory among the 3 biomarkers in terms of identifying the likelihood of recovery. It turns out that if measurements are taken over the first 72 hours following an injury, it's possible to construct significantly better predictions by taking the maximum over that period, instead of, let's say, just looking at the values of GFAP at the beginning. Because the sample size was small, we would recommend that investigators consider a follow-up study with a much larger group of subjects before committing company resources developing a commercial SNAP test. Before we go into the takeaways of data visualizations in general, let's spend a few moments in saying, okay, if we would provide a recommendation to the company in terms of how to design a larger study, let's try to identify what are the first 5 key features that we would like to expand the study, or what do we want to see in the study. So if we have to provide a recommendation in terms, okay, bigger sample, all right, what else? Age, so we want to measure age for each one of them. What else? More cities. A control group, we have to talk about what control group would mean in this case. Nutrition, I'm seeing some income, race, the breed of the dog. Comorbidities, excellent. nutrition, lifestyle, size of the dog. Excellent question. Exercise. What is the level of the activity? Type of accident. So body fat percentage, level of happiness. That's interesting. That would be very hard to measure though, right? How would we measure happiness? All of these are excellent comments. And some of them, yeah, make me think, how could we measure happiness of the dog? Especially in a moment right after having an injury, probably it's hard to, but perhaps we can try to reconstruct it by looking at the history and the type of family that the dog lives in. Tail activity. The movement of the tail per second. Geographical locations, indeed. Well, all of these are excellent standpoints. So the goal of a larger sample size would not just be to have more data points, but perhaps to have a more representative type of sample. A sample that perhaps can be, we say, stratified across all these different dimensions. And anything that reflects the quality of life, the level of health, and the level of health can come from age, comorbidities, level of exercise, and so on, but also the level of mobility of the dog. A dog that is probably very active might have higher chances of recovery. However, we have to consider also that dogs that are very active, if they sustain an injury, they also have to be put, they need to be helped so that they don't make the wrong movement and injure themselves even worse. You know, there are a lot of situations that we need to consider. So having a sample that can be stratified, that is, if we gain this type of information, we can conduct specific analysis for specific groups, we can run multiple tests, we can consider the age factors and so on. So the classification problem can become potentially much more effective, and the use of the test will be in conjunction with the biodemographic type of data relative to the dog, and can help us come up with a better representation. What about how would you be able to use the tools that we have learned today? So the 1D scatter plot, the 2D scatter plot, the line comparisons, and so on. If we, let's say, we have age and location. If we had location, let's say, what kind of tools would you use? A heat map. Now, what would be the drawback of using a heat map in this case? This is an important concept. Let's stop for a second at the concept of heat map. So imagine that you have a large geographic area and you're looking at an extended period of time. Why the heat map can be potentially misleading? Do we expect that the dogs are uniformly distributed in a geographic area? Exactly, John suggests volume. The density of the dog population might be different, right? So where there are more dogs, you have a higher chance to see an accident of this type. Natalia, that's a great, excellent point. Just looking at the recovery variable is not telling us the full story. That's beautiful. In the sense that there might be a lot of intermediate cases, that is, dogs that only partially recover. So perhaps not just recording whether the dog is walking, but also the way that the dog is walking can actually give us a better idea of how full the recovery can be. You are an amazing group of students, and You have great intuition and great ideas. Can I hire you all as research assistants? Can you work with me? Can you help me? Herman, the vet clinic distribution. Indeed, the proximity of veterinary services to the location where the dogs live can be very important because it can tell us a lot about how likely it is that those dogs were getting medical treatment. So, excellent. What about if we wanted to use age? What kind of graph we would use if we had age and the possibility of recovery? One-dimensional scatter plot, okay. Very good. So histogram could be interesting. Having two histograms by age for the ones that recovered and the ones that did not recover. And what about if I wanted to look at the relationship between biomarkers and age? The two-dimensional scatter plot, right? Excellent. I think you are all getting it. Oh, you're very fast, but I did see a comment that says, well, the pregnancy status of female dogs might actually help, might be an important factor in determining the chance of recovery, and that's absolutely true. And of course, the type of accident. The severity of accident can really help us determining the severity of the injury and how badly, you know, the spinal cord is also a very complex type of injury, can happen in different portions of the spinal cord, and perhaps the exact position in the spine where the trauma took place could be an important factor in determining the chance of recovery. Mauricio, in case of death, an autopsy, well, of course, autopsies can provide all sorts of additional insights. Francisco, could it be if the dog is neutered or not a factor to take into account? I'm not sure. That we would have to really ask a domain expert. Other relevant biomarkers, perhaps, although chances are that if those were the ones that we were recommended by the pharmaceutical company to take into account, probably they were the ones that were already studied as potential factors, right? And also, you know, if the dog had previous injuries, right? If the dog, for instance, also had some already existing amputations or other major injuries in the past, of course. So, Laura, data is power, agreed. So let's draw some conclusions, and then we go and take a little break. We evaluated the potential market value of a SNAP test for spinal cord injuries in dogs. What are the takeaways from a data science standpoint? You learn the power of data visualization and also the limitations, how certain plots were masking some of the information, but generated enough questions that we could look at alternative plots types to look at this type of data. So before we try modeling and so on, data visualization can be very effective in helping us understanding the problem. We also learned how to identify potential issues in the data itself through the use of these plots. For instance, how well a biomarker can inform us, or how small is the sample size, how large is the sample size. So very important point. It's recommended to use different type of marker. So yes, for students that are colorblind, red and black circles are not ideal to track. We will definitely follow up this information to the team that developed the case and actually revise the plots. So instead of using just the color, we also use the different symbols. We want that the case graphs and so on, they are accessible to the highest possible number of students. One, thank you very much for this important comment that we need to include it. So we have some of the our team leaders here and definitely follow up and revise the plots. Thank you very much. So here are some further tips that we want to keep in mind. The use of summary statistics can be very important because it can give us some quantitative type of information. However, tables in themselves, they cannot provide the same level of insight that histogram, scatter plot, and parallel coordinate plots can offer. Plots can have an incredible effect in stimulating conversation, and today's class is the proof for that. All of you were able to interpret in a creative way and insightful way all these plots and give a lot of suggestions that were even beyond what were contained in the text. So, and I found we discussed a lot of them because I've been looking at the chat continuously and getting your input and offering you some of my inputs as well. So always include a lot of plots in your reports because they can really can be very powerful tool for investigating the data. Color or different type of symbols can be very important because they provide an additional insight. I want to suggest something else. Sometimes animations are the next level of data visualization. For instance, one of the things when I present maps, I do a lot of work in space-time type of analysis. So how a map changes over time is actually very interesting. So the animation and the sequence of maps can provide even further information. And I also have experimented with sound. So adding sounds to an animation can provide an additional variable that our two-dimensional, three-dimensional eyes can have a lot of issues in capturing. And one day, maybe I will show you some examples. We also learned how to decouple graphs by categories. We looked at graphs separately when we were looking at recovery versus no recovery, male versus female, and so on. So color, we saw that color was used effectively to have different types of dots, but also for heat maps, although color sometimes can be challenging for some of us to visualize correctly. And as one pointed out, the use of symbols can provide a similar type of information content, at least in some examples. But in heat maps, although we might not use necessarily color, we can use scales of grays, because scales of grays give us different intensity, and even a person that cannot distinguish different types of colors can still be able to distinguish different gradation of the same color. So same scale of gray, gray scales could be used effectively when color is not an option. Sometimes, for instance, if you have only a printer that is available that does not have color, it can only print in black and white, shades of gray can provide similar type of information, okay? So data visualization are a very important part of decision making. It's very recommended not just at the investigation process, but also when you're trying to make a case, when you're making a report, when you're trying to convince somebody about the relevance of your conclusion. Good plots take a lot of effort, take good technique to develop, but they are worth the effort. and it's time well invested because it can really make a difference in your model choice, and also help people understanding and approaching data in a way that is less intimidating and that is more friendly. Our generation is very used to process visual information. We grew up with computers, with smartphones, and so on. And a lot of what the information that we get is not just by reading. Reading is very important, but we watch lectures on YouTube, we watch videos, and the way that our minds work is that we are very sensitive to visual inputs. So being able to provide scientific information and quantitative information using plots can be definitely a powerful tool that you want to use. So we have still a few minutes, and the second case is supposed to start at 10:15 your time. However, we have time until 10 o'clock if you have additional questions, or I will let Monica and Oscar decide if we perhaps prefer to give you a little bit longer break, but I am here to answer any question you might have. So I can also go back and scroll up on the chat because we had a lot of questions already. When we should consider dimensionality reduction for plotting, Jorge? Well, Jorge, any time that you have multiple groups that you are interested in compare, you might want to start looking at that. Also, when you have so many variables that they are harder to interpret, or they are providing similar information content, then you might want to resort to dimension reduction methods like principal component analysis or factor analysis that can help us telling you, okay, this type of variables as a whole, as a group, can help you predicting this particular outcome. Those are called dimension reduction techniques. Principal component analysis is the typical example. What happens if there are more than 20 variables? Exactly. When you have 20 or more, in that case, you might want to look at clusters of them, or the 20 plots are still reasonable. The thing is that when data sets are large, the number of variables can get in the hundreds or thousands very easily. And that's where you want to use perhaps a lot of machine learning methods that where an individual look at each one of the variables might not be possible. You want to use perhaps a penalization methods that allows you to identify which ones are the most relevant variables, and then you can look at those more in detail once you pre-process the data. Why do we use the +1 biomarkers, David? Because when you want to take the logarithm of certain variables, if you have 0, you cannot take the logarithm of 0 because it goes to negative infinity. So since you can only take the logarithm of positive variables, that's why you add +1 to each one of them. As Isaiah says, the log of 0 goes to infinity, to negative infinity. That's correct. Principal component analysis for redundant variables could be useful too, indeed, because you would be basically collapsing together variables that are similar to each other, or that are highly correlated with each other. What happens when your value is -1, says Andres? Well, Andres, in this case, we are working with variables that should be always positive. We only had one case, which was that -0.3, which was likely a typo or a wrong data entry. Oh, the example of Jon Snow, if it was useful in difference in difference. Yes, difference in difference is a technique that actually can be used whenever you have an area, let's say, that is not, you could define an area that was not connected to that particular water pump, and then perhaps check the rates of cholera, indeed. Jorge, is it a good practice to fill missing value with some kind of interpolation? It depends. If you have information about those missing values, then yes. Methods like predictive mean matching or other time series interpolation techniques could be used if you have reasonable values to use as potential interpolators. In a map sense, interpolation is used all the time because you cannot measure take measurements at all locations. So a lot of what we do in spatial statistics is actually interpolation. How many subjects would you need a proper conclusion in this case, asks Diego. Again, it really depends on the variability of the population. So if we know that spinal recovery in dogs can be altered or can depend a lot by age, we do need to have representation for all ages. If we know that it has that it depends on the breed, then we definitely need enough samples for each breed. Again, the sample size is really connected to the variability and the heterogeneity of the population that you are studying. If you are studying a population that is reasonably uniform, that is very similar to each other, you don't need a large sample size. However, if your population has many subgroups, many heterogeneities, then you need a larger sample size. David, can you provide us tool to develop plots? Absolutely. You will see a lot of cases here dedicated to data plots and to plotting and so on. So, by the end of the course, you will have a lot of experience in many types of plots. Brian, what are the most common problems that we can have in a data set? Oh, there are so many issues that you can have in a data set. Well, now, first of all, we want to assume that data sets are, properly processed and that the data is properly cleaned. Unfortunately, that's not always the case. The biggest problems are when data are mismatched. When you have that the rows and the columns there have been skips and they are incorrectly attributed, because that can lead you to wrong modeling and wrong conclusions. Then, of course, you might have that the data is inconsistently measured, or you have qualitative variables that have different ways to indicate the same category. There are all sorts of issues that you can find with data. So data cleaning is actually very important. Juan Pablo, are there pitfalls with having more data? Well, you would be busier analyzing them, at computational times can technically go up. But more data means more information. So the benefits of having a larger data set always encompass any inconvenience of having to analyze a larger data set. Lizette was asking why logarithm scale to plot data. Just because the data were so sparse, and you have a lot of data in this case that were on the smaller scale, we wanted to really, the log in this case was acting like a magnifying lens to look at the small data in more detail, because otherwise they all looked like they were almost zero because you had some very extreme values. So in that sense, the data were transformed into the log scale because the log makes the large values smaller and the smaller values comparatively larger. Moises says, do you agree with this? Data scientists spend 80% of their time cleaning data rather than creating insights. Data scientists only spend 20% of data creating insight, the rest of wrangling data. Well, this type of sentences, reality is always more nuanced than this. Data scientists, first of all, a data scientist can have many different profiles. And really depending on your place of work and the type of duties that you have, you might fall in any of those groups. Ideally, any type of company that deals with data should have data collecting protocols that limit the amount of time that is needed in cleaning data. If you have a good data collection protocol, your data set is going to be very well organized in such a way that you do not need to do too much cleaning for the data. Regarding the data wrangling versus insight, that's a genuine concern because data collection exploding in this day and age, so we have so much data, we do have the risk of getting a little bit lost. And this is why before analyzing data, it's important to get knowledge so we know to start being selective about the type of data that we want to analyze, to try to be more mindful instead of just using anything that for which we have values for. Andres, yes, the log scale in this case is the natural log. How should you deal with outliers before modeling, Alex asks. Well, the problem of outliers, which is actually treated in one of the cases, if I remember correctly, it really, really depends. Also, defining something as an outlier is not always a straightforward answer because there are truly veritable outliers that are essentially mistakes. When a value is impossible to be observed in that sense, then it should be deleted. However, if the outlier is just a number that is very large and that it can happen, and then there are multiple ways that you can address it. For instance, using heavy tail distributions. So distributions that allow for high likelihood of observing extreme values. And there are many of them, the Cauchy distribution, the T with low degrees of freedom, the Cauchy, the Pareto distribution, and so on. Catherine, two D scatter plots are still clear to me. Any recommendation or example to explore more about the application? Check the link that is in the case. However, I can definitely, if you email me on the on Snapchat later on a private message, I will send you additional sources to look at two-dimensional scatter plots. Juan Pablo, I still don't get why there are different scales of color red, black in each plot. What do they mean? You have a pink instead of a red when you only have two measurements, when the data is not, when the data was not complete. Although we do have also some gray lines. Yeah, I cannot quite remember if there was another issue as well. Christian, sorry, I'm a bit late. These values mean time blood or something different? They are markers in the blood. They are biological variables that were measured in the blood to determine, determining the chance of recovery from spinal injury. Okay, we are at time now. Thank you very much for a very animated discussion, and I will see you in about 15 minutes with our coding case using pandas.
Thank you so much, Professor Gavino. So guys, go grab some coffee or tea or something. Remember that you have like 15 minutes break, and then we'll be back with Professor Gavino for more, data science knowledge, this time with pandas. So keep on going here, guys. See you in 15 minutes.